Hello all, hope you're doing well. So we are going to discuss few questions of acid, bases and salts since we have already finished discussing all the topics of this chapter. So one by one we are going to discuss. Now first question, which of the following is a normal salt? Now if you see over here, these options over here, PbOH whole Cl, this is like has a replaceable OH ions. This has a replaceable H positive ion. And then if you see this is calcium bicarbonate, this also has a replaceable H positive ion. So any salt having replaceable OH negative ion or H positive ions, these are called as base salt. So this is nothing but base salt. So this is your acid salt because it's having replaceable hydrogen over here. This is also acid salt only. So now coming to the C option. So normal salt is one which doesn't have any of these. Any of these meaning not even the replaceable hydroxide ion, not even the replaceable H positive ion. So this is our normal salt. So C option is correct. And if you see it properly, like if you just want to make it under normal salt, we have acidic, basic and neutral salt. So if we see this, this is obtained from the parent acids, acetic acid, and parent base is NaOH. So strong base and weak acid. So it's going to be basic salt. So if you want to clarify, go into that part. See, whenever you're doing some question, it's an objective. So you always try to look at the options. We always try to nullify any two options or three options. So sometimes there is always a confusion between two options, and the two options are always like incorrect. That you can figure it out easily from looking at the question if you have studied well. Now, sometimes what I believe is like even if the wrong answers are there, right? So it's always better, just have a debate on those options which are not correct. You'll get an additional information, right? So always try to look at the question not from just answering purpose. Try to look at the options, what these options mean, how we can look at it, or do we know about these options or not. So sometimes they give any random statement which is, you can say, not related. So but still you can always search online, you can ask your teachers, you can always have an added information that gives you, you can say, it actually gives you a boost of confidence. So there is no harm in that. So moving to next question. So, which of the following is not a monobasic acid? Now, what is monobasic acid? Monobasic acid is the one which is having basicity. Basicity is nothing but the replaceable H positive ion. So, basicity is 1 over here, right? So, let's write the formulas of all the options over here. Hydroiodic acid, that is HI. HI, you can look at the formula. This is having only one replaceable hydrogen, so it's mono basic. But remember, all they are asking you about the not a monobasic. See, always try to highlight not a, in or incorrect. These terms always try to highlight, because when you are on a roller coaster ride, when you are having some 100 questions or 200 objective questions in the competitive examination, so you misread these small terms, and they are the important, you can say, aspect of any question. Incorrect, correct, not a. So people, most of the students, they just don't look at this, you can say, these small things, and they always go for the other way around, and that leads to incorrect answers. So always try to have patience when you're reading a question, always look through it. Then not a monobasic, so HI is a monobasic, so it's not our answer. Then hypochlorous acid is HClO, so that is also having only one replaceable hydrogen ion, so it's monobasic again. Formic acid, formic acid is HCOH. This is also monobasic. If you remember, this is, you can say, HCOO minus. This is something called as formate ion and H positive ion. So if you open the structure over here, here. So this, you can see, I might have told you before also. I'll be taking up one more lecture where I'll be discussing some extra topics where of this chapter again, and I'll be discussing about few structures of acids and even theories that I'll be uploading soon. So this, if you can see over here, like this bond is a covalent bond, but this is non-polar because the difference in the electronegativity between carbon and hydrogen is negligible. So this again I've taught in the, you can say, polar and non-polar covalent bonds lecture. You can just look at it in my channel. Then if you see this part, this OH, this is very much polar, right? OH bond is polar because the difference in the electronegativity value of hydrogen and oxygen is more, right? So it's a polar bond, and polar bonds are mostly reactive. Non-polars are not reactive. So obviously the hydrogen which is bonded to carbon is not going to replace, but hydrogen from oxygen is going to replace, and that leads to formation of one H positive ion when you are going to add this formic acid in the solution. Now coming to oxalic acid. So oxalic acid is COOH whole twice. So if you open the structure over here, so it's something like this. So carbon can form bond with its own bonds, with the, not own bonds, like with itself. So something we call it as catenation, that we'll be covering up in carbon compounds. Now, if you see over here, like again, we have two hydrogens and they're bonded to oxygen. So these are very much polar bonds. So if they are polar bonds, definitely these hydrogens are valid enough to be replaceable in the presence of water. So that means this is dibasic. So oxalic acid is very much dibasic acid. So that's our correct option. So again, you need to have a prior information about the chemical formulas, about the basicity of different acids. Then only you can answer this. Otherwise, there's no point. Moving to the next question, which of the alkali hydroxides is most basic? Now, I want to add you can say, a concept over here which we haven't studied, at least I haven't taught on my channel as of now. So, we have this lithium, sodium, potassium, rubidium, cesium, and francium. So I'm not keeping hydrogen at the top. That's not important for us because hydrogen doesn't have any properties similar to this group. So this is group one. If you see the periodic table, your extreme left, the very first vertical column that you see, it's a group one, right? So now, francium we are not going to consider. We don't even have as an option. So we say that when you move from you can say down the group, when we move from top to the bottom, basic character increases. So why it happens, that we can discuss in the periodic classification later on, but at least as the question is required over here, these are all bases and we need to find it out which is the most basic over here. So when you move from top to bottom, so the very first answer that comes to your mind after reading this question is potassium hydroxide, right? So then you might be okay, you can relate to that, that reactivity order, if you remember, of metals that we discussed in chemical reaction and equations. So again, potassium hydroxide is not the basic, right? At least according to these options. Lithium hydroxide is also not there. Sodium hydroxide is also not there. So it's cesium. So if you can see down the group, basic character increases. So if we compare all the bases, cesium hydroxide is the most basic one. Francium we are not going to consider because it's a radioactive metal. It's very unstable. Radioactivity we can discuss later in any future videos, not over here. So that's the answer. Now coming to the next one. Noble metals are dissolved in what? So now this again we need to have a prior information that noble metals, like if we talk about gold, we have platinum, right? So these are noble metals. These are not so much reactive, but we should not keep this in our mind that they don't react at all. They can react with oxygen, but at a very slow rate, something that is not basically visible. So let's say if you have gold jewelry, right? So after a certain period of time, the shiny surface of gold, or you can say the shiny, it's extreme yellow color. So it actually becomes dull if we are wearing it for longer years, or after a certain period of time. So why it becomes dull? Because of the deposition of, you can say, oxides or any kind of compounds on the surface. So that needs to be cleaned enough. So Remember that this gold and platinum, this, can be dissolved in a very specific ratio, and that is aqua regia. Aqua regia is nothing but 3 parts of HCl and 1 part of HNO3. So it's not only nitric acid, it's not only HCl, it's not only sulfuric acid. We don't have sulfuric acid in the aqua regia, we just have HCl and HNO3. So 3 is to 1, that is the ratio for this mixture of acids. So we have to take only these two acids. We are not going to take sulfuric acid. So the answer over here is aqua regia, and this is also in some cases called as royal water. So it can dissolve noble metals. Then we come to the next question. So the amount of energy released in neutralization reaction between strong acid and strong base. Now again, with the help of this question, I want to explain one concept. First, we'll define heat of neutralization. See, neutralization reaction, I might have told in the chemical reaction and equations that it's exothermic in nature. That means heat is released over here. So now we actually use a term H that stands for heat content. Now I'm trying to explain a concept which I haven't taught before. So it's something that you study in your thermodynamics chapter. It's enthalpy. It's you can say this heat content is something called as enthalpy. So enthalpy meaning only heat content. Now what it is, like, let's say you have an open test tube and you're doing some reaction. So it's an open test tube, so it's happening at a constant atmospheric pressure wherever you are doing that. Then we have certain reactions that can be taken place in the closed container. So over there the heat content will be different, but the heat content in the open, you can say, test tube are going to be different. So that heat content is something we call it as enthalpy. So I'm just trying to make you understand, you can say, from a simple term we can define, you can say, this heat of neutralization. So we in a more precise term we call it as enthalpy of neutralization. So it's a thermodynamic term. So now coming to the neutralization, we know it's exothermic. So this enthalpy we never study as simple H. We always try to study in terms of change, right? Delta over here stands for change. Just like you do this delta T, change in temperature. So delta H is change in enthalpy for whatever reaction you are studying. But we know that why we introduce this kind of, you can say, term at the first place, because we know that most of the chemical reactions happen in the open atmosphere, right, in the test tubes. So in the closed container they are not so much, you can say, in number. So now the change in enthalpy, we always try to put it as negative for exothermic reactions, because heat is released, like you have a room and some heat is inside. So if you open the door, so it's going to be released through that door. So you compare it to the initial enthalpy or initial heat over there. So it has reduced now, because you have allowed that heat to release from the door. So now that's why the negative value, so it has decreased because you allowed it to release at the first place. Then delta H can be positive for endothermic reactions. So endothermic reaction where heat energy is absorbed, where you are supplying heat energy to a particular system, to a particular reaction. So you're adding up the heat in that, right? So addition of heat, just like if you have a closed room and you have a heater in it. So you're increasing the heat content of that room, and provided like that room is closed and it's not releasing continuously. So always remember, if you have and how do we calculate, like what's the unit of this? So it's kilojoule per mole. So most of the reactions that we come across, you always have some value around it written in the form of negative and positive. So negative meaning that reaction is exothermic, positive means it's endothermic. So you can remember it. Now coming to the enthalpy of neutralization. Now what this is. So enthalpy of neutralization is an enthalpy change when an acid and base react to form 1 mole of water. So it's always negative, right? We have to remember that. So it's always negative. So heat is released during this, that's why it is negative, right? Now, coming to the main part, for the strong acid, I'll come to the question. So I'm just giving you background information. So if you have a strong acid and strong base, the enthalpy of neutralization is a constant value. So for strong acid and strong base, we have somewhere 57.3 to minus 57.62 kilojoule per mole, or we even have in kilocalories per mole, so minus 13.7 kilocalorie per mole. So these are the, you can say, for a strong base and strong acid. This was given by Hess in somewhere in 1840s. So this is this is for 1 mole. Remember that we are talking about 1 mole. So if the number of moles of water formed are going to be increased, if it is doubled, so this value will also be multiplied by 2. It will be doubled. So protic acids, if we say diprotic acids are the ones like dibasic, right? So they can replace two H positive ions, right? Or you can say dibasic means two replaceable H positive ions. So diprotic means they can release two H positive ions in the presence of water. So it's the same, it's a similar thing only. So acid or base, so you can say in this case how many you can say moles are formed. So it's double the, so it's you can say, or you can just say heat of neutralization is doubled, is doubled as 2 moles of water are formed. Right? So, coming back to our answer over here. So, the amount of energy released in neutralization reaction between a strong acid and a strong base is going to be what answer? So if you can see this, we have 57.62 or 57.3, right? So point 3, we can actually go to the point 1 also. So I'll correct this. Like we can point three, it varies because this is a range for kilocalories. We don't have a range. So you can just write 57.1 also, 57.3. So I'll just correct it 57.1 over here. That is okay. So if you can see over here, the options given over here 57.8. This is not our answer. 57.1 is, you can say, the nearby answer. 57.9 is like too high. 56.1 not optional, like it's, there is no option for that. So the correct answer is this one. So I hope you have understood this concept. Now apart from this, I want to explain one more thing. Is like, if you have a strong acid, a weak base, or vice versa, then the heat of neutralization is less than the value for strong acid and strong base. So what's the meaning of this? What is the meaning of this? Meaning is that if you have a strong acid, let's say strong acid HCl, and weak base, we can take ammonium hydroxide, right? So the strong acid and strong base standard value is minus 13.7 kilocalorie per mole. We know that. Now, what will happen, since one of the counterpart, like one of the base or acid is weaker, right? So, since it's weak, it won't completely ionize. It will have trouble ionizing itself, right? It will partially ionize. So, because it's you can say partially ionizing over here, because of the partial, you can say, ionization over here. So now the value released, you can say the heat energy released will be lower than this. So lower than this value, the standard value. Now why is that? Because some amount of heat energy which was supposed to be released in the case of strong acid and strong base, it is getting released over there. But in case of strong acid weak base, or weak acid strong base, what is happening over there? Some amount of heat energy is going to be taken up by those weaker counterpart in order to ionize itself. Because they are weak, they won't be able to ionize at the first place. They will utilize that supposedly released energy in order to ionize. So you can just, it's a hypothetical value that I'm giving over here. So minus 13.7, right? Hypothetical I'm talking about, it's not related to this one. So let's say some heat of ionization, let's say the, and heat of neutralization. So the heat of neutralization for this particular, you could say, reaction HCl plus NH and ammonium hydroxide, this gives you this. So this will give you ammonium chloride and water, correct? So heat of neutralization over here is, let's say, minus 13.2 kilocalories. Like this can, this is observed. I'm just talking hypothetical values, these are not standard values. So minus 13.2 kilocalories per mole. And the heat of neutralization for a standard, you could say, for a strong acid and strong base is minus 13.7. You subtract it. So minus 13.7 is the heat of neutralization. You subtract minus 13.2 over here. So this will give you minus 13.5. So this is the heat of neutralization for this particular reaction. 13.5 is a heat of neutralization for this particular reaction. So, sorry, my mistake. It's zero point 0.5. Okay. So zero point 0.5 kilojoule, kilocalorie per mole. So now I'm trying to explain again. So we have a standard value 13.7 kilocalorie per mole. Then we have a reaction, let's supposedly this reaction, and we have 13.2 kilocalories per mole as a heat of neutralization for this reaction. Right. Now if they're asking you in a question that what is the heat of ionization involved, then what you will do? You will subtract the standard heat of neutralization that we already know, subtract the actual heat of neutralization, then you will get this value 0.5, and that is going to be, you can say, minus 0.5. So if you see this 0.5 value, this is nothing but heat of ionization, this one. So this much amount of heat is going to be utilized by the weaker counterpart in order to ionize itself. That's why there is a change in the heat of neutralization value when you have any one counterpart as a weaker. So I hope you have understood this part. Now coming to the next question. Solution of PbOH whole Cl in nature is what? Now again, if you can see one thing, they are asking you about the solution. So we know that PbOH whole Cl is obtained from lead hydroxide, which is going to be weak base, and a strong acid, which is HCl over here. So from the radicals you can see over here. So since we have a strong acid and weak base, so the solution of this should be acidic. See, now you might be thinking, okay, it has replaceable OH, right? So why we are calling it as acidic? Because they are asking you about the solution. They are not asking you about the salt, that PbOH whole Cl is a base salt. They are saying the nature, like in terms of pH. So we have to add the solution, we have to add the water. So in that case, yes, it is as acidic, because then you have to see its parent acid and parent base over here. Then we go to the next question. Which of the following is a basic salt? Now the basic salt, so again you have to see its parent acid, parent base. So tin chloride, so this is definitely weak tin, right? See, most of the strong bases that you get is in group 1 and group 2. We don't have many strong bases, or you can say even soluble bases in terms of D block and F blocks. We have majorly over there. Then NaCl, okay, this one is HCl. So this is acidic, because it's obtained from weak base and strong acid. So this is acidic. This is NaOH and HCl. This is neutral salt, NaCl. Now this one, this is our answer. This I have done before also. This is acetic acid, which is weak acid, and we have NaOH, which is strong base. So strong base, weak acid, making it as our answer basic salt. Now if you want to see that, this is acidic salt obtained from ammonium hydroxide, which is weak, and strong acid, HCl. So this is our answer. Now we come to the next one. H3PO2 and H4P2O7 are respectively what? Now this I might have told you in the basicity part as an exception. I still haven't discussed the structure over here, but still we'll be doing it soon. So H3PO2 is monobasic acid. It has one replaceable hydrogen in spite of having three. Again, the concept of polar and non-polar bonds are involved over here. So we'll be seeing in the structure later on. The H4P2O7, we can even discuss this structure also in the additional topics of this chapter later on. This is tetrabasic. See, tetrabasic, or you can say tetrabasicity, can also exist. An acid can release 4H positive ions also. So the answer for this option is monobasic and tetrabasic, right? Then coming to the next part, mixture of two pure acids, the strongest acid will be what? Now, now in this, I want to add one thing. This doesn't apply always, but higher the oxidation number of central nonmetal of acids, higher is the acidic strength. Now, if you see over here HNO3, now let's try to calculate the oxidation number. Now, for oxidation number, if you don't know, you can see my video on my channel, oxidation number. So this nitrogen over here is +5 oxidation number. Sulfuric acid is +6. So sulfuric acid, sulfur oxidation number is +6. Now, how do I calculate this? You can see that video. Okay, boric acid is +3. This is +6. Boric acid by default, it's a weak acid. It's also used, I might have told before also, this is also used in your eye drops. It's a boron compound specifically. So then perchloric acid, this is +7 and +6 again. So now you think that mixture of acids, pure acids, the strongest acid will be what? So higher the oxidation number. We have only one option where both of them are having high oxidation number, and that's this one, +7 and +6, if you can see it. So this is our answer, right? So again, if you want to learn oxidation number, how to calculate, please check that video. Then we go to the next one. Now Na2HPO4 is what? See, you have only one replaceable hydrogen, if you can see the formula. So it has to be monobasic acid salt, right? So over here, HPO4 2 minus ion and Na plus is monovalent. So you can see this is having one replaceable. So it's monobasic acid salt. Why acid salt? Because it has replaceable hydrogen over here. Monobasic, why? Because it has only one hydrogen over here, so that it can replace in order to form like the next step. The next step will be what? Na3PO4, right? So if you replace hydrogen out of it, it will be sodium phosphate formed over here. So this is obtained from this acid H3PO4. H3PO4 is not going to just release all the 3H positive ions in one go. It's going to be a step-by-step process. So H plus, then you have H2. So this is H2PO4. Right, so this is going to be minus. Then if you have H2PO4 minus, you want to release one H positive ion, so this will be HPO4 2 minus, because you released one more H positive over here. Then if you go to the last, HPO4 2 minus will change into one H plus and phosphate radical is going to be formed. So this is how we can write the equations for this tribasic acid also. Okay, so this is the answer. Next, which of the following represents the correct order of the acidic strength for equimolar aqueous solution? So equimolar, molarity we still have to discuss. That will be uploading soon. So equimolar means same concentration. Same molarity, same concentration. Molarity I still haven't introduced, but we'll do it soon. So now, equimolar means that means the concentration is not changed. Since concentration is not changed, so we can actually find the acidic strength. So we have to find the correct order. So we have to use our brain over here in terms of like understanding which will be a stronger acid and or not. So see, pH is you can say it's like it's the correct order we need to find. So see, the first option, if you see over here, we have HCl starting over, right? So its pH is low, and then they are ending with H2SO4. Its pH is also low, so that means this is wrong order. Then they are starting from a weak base, going to the strong base. Then their strong base means its pH is, you can say, acidic strength, right? So correct. So acidic strength, no. So this acidic strength is going to be, you can say, lower. Yeah, NaOH acidic strength will be lower than ammonium hydroxide because NaOH will be falling towards a pH of 14 and NH4OH will be somewhere, you can say, near to 7 or somewhere in the weaker section of the pH. If you remember pH, if you don't remember, please watch my videos. Then acidic strength. So now if you see this H2SO4, it is having +6 oxidation number. Its acidic strength will be higher than HCl, right? So this is wrong. This is also wrong. Now coming to this one, fine. Acidic strength again. So they are moving towards NaOH. Definitely its acidic strength is not stronger. So this is also wrong. So coming to our last option, and which makes sense, you can say NaOH, which is a strong base, its acidic strength will be very low. Then ammonium hydroxide will be somewhere around 7 to the weaker section of the basic part. So its acidic strength will be slightly higher. You can say, at least if you are studying the order. So slightly higher because it's, you can say it's a weak base. Weak bases will have slightly higher acidic strength compared to stronger bases. Then HCl, then H2SO4. So HCl and H2SO4, sulfuric acid will be more acidic strength because of the higher oxidation number. So this is the correct option. Then we go to the next. Substance A reacts with another substance B to produce C. So whenever you get these equations, then please write like this. So we have ABC, we don't know what ABC stands for, and a gas D is formed. So D is a gas that we know. So if a mixture of the gas D and ammonia are passed through an aqueous solution of C, baking soda is formed. So if a mixture of gas D and ammonia through a solution of C, then baking soda is formed. Baking soda is nothing but sodium bicarbonate. Now, if we talk about this reaction, this is reaction of Solvay process, right? So we have gas D and solution C. So we have to look at the options. So they are asking substances A and B are what? So if we go back to the Solvay process was ammonia reacting with NaCl plus water plus carbon dioxide giving you sodium bicarbonate, and there was a secondary product that is ammonium chloride. So we need to have a background information of this reaction because they are talking about baking soda. So now D is a gas, so this has to be carbon dioxide, ammonia. Then solution C they are talking about, that has to be brine solution, NaCl and water. So this is giving us baking soda. So that means over here this is NaCl and over here this is carbon dioxide. Now we got the products, now we have to find the reactants. So from where we can get this, we can say, these two products. So looking at the first option, if you can see, HCl and NaOH will give you NaCl and water. So it's not giving you carbon dioxide. This is wrong option. Now if you go to the second option, HCl and Na2CO3. Now this is NaCl and water and carbon dioxide. Whenever you take a carbonate in the chemical reaction, it will always give you a carbon dioxide on the product side. So this option is valid. Now Na and HCl, since we have to prove other options wrong, Na and HCl will give you only NaCl and hydrogen gas is formed. Hydrogen gas is not required for baking soda at all. Then Na2CO3 and water, if you talk about, This is again like aqueous solution of sodium carbonate, so it's nothing helps. So the correct option, that feasible option that we have over here is B. So A is HCl plus B is Na2CO3. This is the correct option. So you will get NaCl and you will get water additionally, which they haven't mentioned. That's okay. So coming to the next part, when a compound A is heated and a gas B is evolved, which turn lime water milky. So I want to stop over here. So the next question I'll be doing in a separate video. This is like too lengthy for my great students out there. So I'll be stopping over here. Please subscribe my channel, like my videos, and share with your friends if it was helpful. Then I'll see you in the next video. Thank you.